All right.
You're getting that YouTube ad money for calculus videos.
Yeah, right. I don't think I can do that. I don't think I could. I don't think the school would let me do that.
Make us watch ads. You're not getting them.
No, they used to. You have to meet some threshold of, I don't meet the threshold of it. But even if it did, I couldn't profit off of it.
Yeah.
If I'm on campus using, this is all my equipment, but if I'm, on campus using the facility, I can't profit from that. So, all right. So we have your first mini exam is due on Monday, right? And I told you I would have your next one ready to go, right? So I have that for you, I believe. Yes, I do. And I don't know if I said this. I didn't put it in the instructions, but your work is supposed to be done on separate paper, right? Like I don't give you enough space for these, for you to do the problems here. So here's your next one. I'll let that get around. And as that's getting passed out, let's pick up where we left off last time. We were talking about vector equations of lines and planes, right? And I do not believe we did this example, right? Example 6, where we actually found the vector equation of a line through the intersection of two planes. I don't think we actually did this problem. So let's start off by doing this. I think we talked about it, but we didn't, like how you would do it, but we didn't do it. All right, so what we have are two planes, right? And let me let the test get around, because there's something really important, especially on this next test, when you're approaching the problems, how you approach them. And I think I can kind of illustrate that with this problem here. So look at the question here on the board. Find the vector equation of the line, right? Find the vector equation of the line. Okay, so what are we looking for? We want to find the vector equation of a line. So we want at the end to come up with some vector equation of a line. And so you need to know, what is the vector equation of a line? This is the vector equation of a line. It's a vector function where r naught is a vector that represents one of the points on the line. T is your scalar that basically creates all the vectors on the line. And then v was our, do you remember what that was? So r naught comes from a point on the line. This is our direction vector. If you write down what you're looking for to start, I think it helps dictate like how you approach the problem, right? So I want to eventually find a point and a direction vector that represents a line. Now the line we're looking for is the line of intersection of those two planes. So we had talked about this in class last time. If we have two planes that come together and hit each other and form a line, we're trying to find the vector equation of that line. So let me start by first talking about a point. Can we find a point on that line? Well, a point on that line would have to be a point, an x, y, z, right, that satisfies both of these plane equations at the same time. So can we find an x, y, z? So for the point here, for the point, we need to find an ordered triple, x, y, z, which satisfies both plane equations simultaneously. I think I'm misspelling that. Is that right? Simultaneously? I think it's right. Okay, who cares? It's not an English class. Yes?
For planes, are they written in any other type of format, or is it just like X, Y, Z?
They can be written in vector form as well, but I said last class that we would be doing that in a later chapter.
You know about the hats?
Yeah, vector form.
Yeah.
Mm-hmm. Okay. Everyone understand how I'm approaching this? I'm trying to find the equation of a line. What do vector equations of lines look like? This. What do I need for that? A point and a direction vector. To get the point, I'm just going to figure out, since I know the line is where the two planes come together, right? We have our two planes that hit each other. This is the line we're looking for. We're trying to find any point, right? Any point. Doesn't matter what point it is. Any point. So to do that, you have choices. Yes?
If it's a point, what does R naught have the vector symbol above it?
Well, no. I said this vector comes from the point.
Okay, gotcha.
So we get the point, and then we create the vector from that point.
Gotcha.
Yeah, I'm not saying that that's a point.
Okay.
So yeah, I'll put here from, right? That will come from that point that we find. All right, so any ideas on how we can find a point that would live on both of these planes? Set one of the variables, any one you want, equal to 0 is a nice convenient one. So what would you like me to do?
We actually did it this last class.
We did, right? We did z.
It said Z equals 0.
Okay, but let's do it, right? So I'm going to set z to be 0. And when we do z to 0, we get x plus y equals 5, and then we get 2x. We didn't do the whole thing. We did parts of the problem, right?
We found all the variables.
And we for sure found the point.
Yeah.
Yeah.
So we had that system of equations, right? If you replace z with 0 in both of those, we get that. And then I solved that. Do you have that written down? What did we get here?
X equals 5.
It was 5, 5.
Y equals 0.
It was y is 0?
Y is 0.
Y is 0, and then, of course, z was 0 because why? Because that's what we started with, z being 0. So that was done in class last time, all right? And then this gives us the point 5, 0, 0, right? And then what I'm going to do is I'm going to convert that to the vector r naught, and that'll be the vector 5, 0, 0, like that. All right, so we have our vector that takes us to the line, right? That gets us from the origin to the line. Now what we need is a direction vector. And that means we need a vector, any vector we can find, that runs parallel to that line. And we said we would get that from what? Taking the normal vectors of each of the planes and crossing them. And when we cross them, we would get a vector that's pointed down the same direction as that line of intersection. And I showed that to you. Are y'all okay with that? Sure? Okay, so now I'm going to be looking for the direction vector. So for the direction vector, what we're going to do, that's going to be the vector v. What we will do is we will take the normal vectors of each of the planes. And how do you get the normal vectors for a plane? The coefficients of x, y, and z, right? 1, 1, 1. And when we do that, the x, y, and z, they all have to be on the same side of the equation. All right? So move all your x, y, z's to one side and then take the coefficients. You can't have x and y on one side, z on the other, and look at the coefficients that way. All right? Bring them all to one side. So 1, 1, 1, and then the other vector is 2, negative 4, 7. And did I cross that already? I feel like I...
I think we did.
Let's cross it, okay? Let's just cross it, just for fun, right? Just so we remember how to do crosses, right? Remember how to do it? I'm going to do 1, 1, 1. Remember I did this like I hat, J hat, K hat thing? And then 2, negative 4, 7. And then our answer, our cross product, is going to be a vector. The first component of this vector we get by covering up the i's and doing a determinant on the remaining numbers here. So this would be 7, take away negative 4. So 7 plus 4, right? 11. And then we do the middle one. And remember what the condition we had to put in negative, right? And we cover up the middle. And we do the determinant on this piece here. So 1 times 7 is 7. Take away 2, which is going to be 5. So that'll be minus 5. And then the last one, let's see, we cover up the last column. Negative 4, take away 2. So negative 6. There we go. So my direction vector v is the vector 11, -5, -6. Or any scalar multiple of this. Okay, I could scale this if I wanted to, but that can't be reduced out, right? Like I can't like pull a number out of all of them. So I think that's good, right? And now we're ready for the vector equation, right? So final answer here is that r of t will be equal to the first vector we have here, 5, 0, 0, plus t times the direction vector of the line intersection of the planes. And that would be an acceptable answer. Okay, that would be an acceptable answer. If you wanted to, you could push the t through and then put everything together and just give me one vector, which would be 5 plus 11t minus 5t minus 6t. That's just pushing the t through to each of those and then adding the two vectors component to component. Make sense? Okay. All right, let's talk about distances. Distances. First, what we're about to talk about here is how you find the shortest distance between a point and a plane. And I had talked about this in an earlier class when we were talking about projection vectors and component vectors, that if we were trying, like if we took the projector, right, and we said, hey, what's the distance from that to the ground, it would just be the z-coordinate, right? But if you just had some arbitrary plane sitting in space here, what would be the shortest distance from that projector to this plane? And that's a much harder question because everything's tilted, right? This is what's going to allow us to do that, all right? So first of all, imagine that we're given a point, okay? The projector, all right? And we're given a plane sitting here in space, right? We can find the shortest distance between them by first, and I'm going to show this to you visually. So here's how we're going to do it. This is a little too big. All right, so first thing, we have, where's my point? There. Okay, so we have a plane and we have a point, and we're trying to find the shortest distance between those two. So the first thing I'm going to do is I'm going to find any other point that lives on the plane. Okay, see that blue point? It's just some other point. It's not special at all, just some point on the plane. Then what I'm going to do is I'm going to draw or create a vector that goes from the point that I just found to the point that I'm given in the beginning, right? I can always do that, right? If I have 2 points, find the vector going from one to the other. All right? Next thing I'm going to do is I'm going to think about what the normal vector of this plane is. The normal vector of this plane, right, is a vector. That doesn't look like it's normal, does it? What the hell? My perspective looks off. Well, that looks off, doesn't it? Something must be wrong with my code. I'm not going to look at my code now. Just that's a normal vector off the plane, okay? So that vector is actually arbitrary, right? It can be anywhere. It's just sticking perpendicular to the plane. So what we'll do is we will, you know what, let me reevaluate this. Why is it? I don't know why it's not behaving correctly. Let me try it again. Okay, here, 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 here. Come on. I think it's still messed up. What the? Yeah, it's messed up. I don't know. Okay, so we are going to shift that normal vector, or sorry, shift the blue vector over. Okay, so we have our normal vector. The normal vector, when we find the normal vector, imagine that what we do is we move it so that it points to the projector, right? So you have your plane here, you got your point, we have a normal vector, and what I'm going to do is move that normal vector on the plane to where I'm actually pointed at the point, right? That's this red one, okay? And the normal vector is either going to go past the point or it's going to be shorter. It might even go pointing in the other direction. That doesn't actually matter. What matters is that we see that from here to this right here, that point is somewhere on that line. Then we move our blue vector, which again, vectors can move. We move it tail to tail like this, and then we do a projection. We project the blue onto the red. And what we're interested in is that distance right there. That distance right there is the component of the blue vector onto the red. Remember, the projection of the blue onto the red gives you this vector. The component of the blue onto the red gives you its length. And so that's what we're trying to find. So formula-wise, it comes down to this. So running through this again, we're going to choose some other point, right? And then what we're going to do is once we choose that other point, we're going to create a vector that goes from the point we chose to the point we were given. We're going to call that B. We're also going to remember that the normal vector is n. And then basically we just need to project B onto n. Project B onto n and then take the magnitude of that, or find the length. So this is the formula right here. This is it. This is what we need. So I'll write that down. The distance, this is going to be off camera, but the distance will be the normal vector dotted with the B vector over the normal vector's magnitude, like that, and then this absolute value of that. So the dot product is going to give us a number, take the positive of that, and then divide it by the length of n. That is the formula for this, which you can look back in your notes and see. Geometrically, does it make sense what we're doing? Kind of? Let's do an example. Find the shortest distance between these parallel planes. Find the shortest distance between these parallel planes. Well, I just gave you a formula on how to get the shortest distance between a point and a plane, right? This is asking for the shortest distance between two parallel planes. So how do you think we should start this? We have a plane, we have another plane that's parallel to it, right? They're running parallel. We're trying to find the shortest distance between those two. The formula only allows us to find the shortest distance between a what? A point and a plane, right? So maybe we should start by just getting a point on one of the planes. So on plane 1, let's find a point. Someone want to tell me an x, y, z that would satisfy the first equation? Something easy?
113.
113. Do you all agree that point lives on that plane? On the plane 1? Satisfies the first equation. Okay, so now what we have is this. We have a point here. Okay, let's call this is P1 here. This one will be P2. This point right here, we're saying is the point 113. And now all we need to know is the distance from that point, the shortest distance, right, from that point to the other plane, plane 2, which means I can use this formula right here. So what we need to do now is we need to use the fact that D will be the normal dotted with B, absolute value of that over the magnitude of the normal. Now, we need to be clear on what we mean by B here, what's B and what's N. So let's start with N because I think it's the easier. N is the normal vector of plane 2, right? Well, you could actually say plane 1 as well here because they're parallel. But going from this, where we got this formula, this right here for us would be the vector 2, 2, 2. Right? That's the vector 2, 2, 2. That is the normal vector of the second plane. So what we've done here is we've created the normal vector off this plane, the second plane. We've created the normal vector off of it. That's a right angle there. Right? And we're going to move it so that it's pointing at that blue dot. That's our n vector. Yes?
Is there parallel? Wouldn't the normal vector be the shortest distance we know?
No.
No?
No, because your a normal vector can be any perpendicular, any vector perpendicular, right?
Yeah.
It doesn't have to be, it doesn't have to point to the next plane, right? Like let's just say I give you a plane, right? And I say, okay, here's a normal vector. Okay, now draw me another plane parallel to this. It doesn't have to be drawn to the tip of that one, right? It can be drawn anywhere. That's why we have to project. That's why we need a projection. We have to project a vector. See, we're going to now create a vector that goes from plane 2 to plane 1, like that. And that's going to be our B. And then what we're going to do is we're going to take that B and project it onto the red one, and that will be the distance. So what's B? We need a vector that goes from a point on plane 2 to plane 1, or to the 113. So for B, let's work on B over here. For B, this is a vector that's going to be from any point on P2 to the point that we started this with, 113. Which again was kind of arbitrary, wasn't it? Like 113, we could have used anything that worked there. So if we're going to have a vector that goes from any point on plane 2 to this point, we need a point on plane 2. Yes?
When we get our normal vector,
Uh-huh.
how do we know that it's like pointing to the like in the right direction of the other plane?
It doesn't matter that if it's in the right direction. Because if you go back when we did vector projections, like let's say I have this vector right here. Let's say that that's our normal vector. And let's say the vector that we're going to project is B. If I project B onto N, I imagine extending N in the opposite direction and dropping a perpendicular like this, and this will be the projection. Sorry, no, I did that wrong. This would be the projection vector right here. This would be the projection of B onto N. So it doesn't matter if N's pointed in the opposite direction at all, because we're still going to project on a line that B vector runs through. That all right?
Yeah.
Okay. Okay, so how about a point on plane 2?
10, 0, 0.
10, 0, 0. Fine with that. All right, y'all ready to give me what B is then? So, the vector B is the vector that goes from this point to that point.
Yeah, so -9,
-9,
1.
1, 3. There we go. -9, 1, 3. Once we have that, we go to this. Go right to this. So that means the distance will be the absolute value of -9, 1, 3 dotted with 2, 2, 2, all of that, over the magnitude of n. How do you find the magnitude of a vector? Square root of the sum of the squares of the components, right? So there's n dot b. Actually, I did this backwards, b dot n, right? Does it matter with dot products? No. It matters with cross products, right? But it doesn't matter with dot because we're taking the absolute value, right, anyway? So, well, the absolute value wouldn't matter anyway, but I'm just saying, like, cross products, that does matter. But we're taking a length or an absolute value, so it's not going to have any effect. All right, you ready for a dot product? So this times this, that's -18. And then plus 2 plus 2. Is that right? No, so plus 2 plus 6. And then all over square root of 12. So the top is -10 absolute value. So 10? So we get 10 over root 12. That's the exact distance. We could get a decimal, yes.
What is B again?
Pardon?
What is the B vector?
Let's run through it geometrically again with my visual here. So we started out with two planes, right? We started out with two planes. I'm just going to imagine there's another one right up here. We started out with two planes. And the first thing we did is we found a point here, 1, 1, 3, right? That's what we did first. And then we said, okay, let's figure out what the normal is. I think that's what we did next, right? We did the normal. We said, okay, there's a normal vector. Okay, so there's n. And that for us was 2, 2, 2. And we kind of imagined that that normal vector could be slid so that it punches right through that point, because vectors can be moved around. Then we said, all right, let's find a second point on the plane, which we said was what, 10, 0, 0? It's surprising how much that floor shakes. All right, now what we did is we created a vector that goes from that blue point to the black point, like that, right? That's B. And to help us see what we're trying to accomplish here, we can move that B vector so that it's tail to tail with the normal. And that way, hopefully it's obvious that if we project the blue onto the red and find that length, that'll be the distance between them. Am I answering your question? So we project, and then we say, what's the component of that, which means the length of that vector, right? Because that right there, the projection of the blue onto the red, creates this vector, which is the projection vector. And we want its length, which is called the component. So when we do the component, we're finding that distance right there. So I think what you were asking earlier was, why not just use the length of the red one? Well, the length of the red doesn't give us the distance between the planes. The projection of this onto it does, though. That's it. Okay, so to recap, if you're trying to find the shortest distance between two parallel planes, you pick a point on one of the planes, right? You pick a point on the other one. You create a vector going from one to the other. You take that vector and you project it onto the normal vector, right? Find that length and you're done. I don't know. It seems really kind of great that it doesn't require any crazy math to do that, right? I mean, what have we done to do that is just arithmetic, right? Some addition, subtraction, multiplication, no calculus, no optimization, no derivatives, minimizing distances, right? It's just simple arithmetic with vectors. All right, so that is how you find the shortest distance between a point and a plane. How about the shortest distance between a point and a line? Point and a line. That's different scenario, right? So imagine you have a line sitting in three-dimensional space, and we want to find the shortest distance between this line and the projector. Okay? Here's how we're going to do that. Start with a picture. First, there's our projector, here's our line. Let's imagine that we kind of float through space and get ourselves into a position where visually for us, from our observation point, it looks like that. Do you think we could do that? No matter where you put your line, there's a projector. You could move around to a point where it almost looks two-dimensional to you, right? You all agree? Okay. So somebody gave us this line, right? Somebody gave us this liner. We have this line, which means we have a vector equation, don't we, for this? And someone gave us a point. So you have to remember, you have that information, right? So what we'll do first, we're trying to find the shortest distance between here and here, is we're going to take 2 points on the line we're given and draw a vector between them. And I'm going to call that vector A. right? So 2 points, do you think if someone gave you the equation of a line, you could find 2 points? Yeah? Okay, so we take 2 points, create a vector A. Then we're going to create a vector B, which is going to be the vector that goes from either one of these points, doesn't matter which one, from there to the point we're given. Next thing we're going to do is realize that what we're trying to do is calculate this distance, which I'm calling just d, right? See, we don't have a normal vector here, right? Like in the plane, we had a normal vector that we could project onto. With a line, you don't have a normal vector to project onto, so we can't attack it that way. But we can do this. 2 points, create a vector. This point to this point, create a vector, and then realize we just want to know what this distance is. And now, where the hell is it? I'm going to realize that this is true, right? That when I create this vector from here to here, I create an angle, right? And if I create this angle, which we'll call theta, just by basic properties of right triangles, I know, whoa, that's not me, right? Like, I don't think it's me. Okay, so this angle theta, right, on this right triangle, we have sine of theta is opposite over hypotenuse, right? Opposite is d, which I'm saying d is this distance. Opposite hypotenuse is not the vector b, it's the length of vector b, right? It's how long that vector is. So do you all agree that this is true? Yes? Okay, so solve that for d. What is d? No, just isolate the d. So multiply both sides by length of b, right? And that will give you, I'm missing what, sine theta there? So all we need to know in order to figure out what this distance is we need to know the length of the b vector. You think you could find the length of that b vector? Yeah, sure. And we need to know sine of theta, but shit, that means we need to know the angle between the vectors, right? Which means we're going to have to go figure that out, right? Do we know how to find the angle between two vectors? There's a formula for it, right? But there's something really, really beautiful that's about to happen, all right? If we see something. We have to see something. Does this look, have you seen this before, almost before? Is there something that had, oh man, what was it? Oh, it was this. If you give me two vectors, let's say A and B, and you cross them and you take their magnitude. Do you remember that formula? No? It was magnitude of A, magnitude of B, sine of the angle between. You're thinking dot product. Dot product, right? Don't confuse it with this one. The dot product of two vectors is the magnitude of the first one, magnitude of the second one, and then cosine of the angle between them, right? So that we had, that was like one of the real important formulas. And then we got this one. Do y'all see that this is this piece right here?